Welcome back to Honors Calculus. In this video, we are going to be revisiting the area under a curve. Technically speaking, I don't have anything new that I want to show you in this video, but this is a good chance to wrap up and bring a couple of ideas together all in a single problem. We know that the integral, the definite integral of a function, is defined to be the area of the region trapped between that function and the x-axis. We know that we can have a positive area above the x-axis and we can have a negative area below the x-axis. And finally, we know that we can use the rules of anti-differentiation and the fundamental theorem of calculus in order to evaluate a definite integral without having to resort to other tools. So with all of that together, we can finally start to answer some questions concerning the area underneath a curve that we weren't able to solve before. Let me get my head out of the way and let's dive into an example. So as an example, I want to find the area of the bounded regions in the graph y equals x cubed minus x. To see what I'm talking about here, let's jump over to Desmos and take a look at the graph of that curve, and maybe even zoom in a little bit. We can see that this is a curve that has some bounded regions and some unboundedness. So, showed up right in front of it. If I look here, I have a region between that curve and the x-axis that has a finite area. I've got another similar curve right here, and then way over here and way over here, the curve is unbounded. So I'm looking at the area between the curve and the x-axis here, the area between the curve and the x-axis there. I don't want to just integrate because this is in fact symmetric. This is an odd function. And if I integrate going across this region, I'm going to end up with 0. And so I have to look at each piece of this on its own. I'm going to focus on the positive branch here. We can do some algebra, it's not that difficult, or I can do some clicking in Desmos to remember that the intercepts of this curve are going to be at 0, 0, 1, 0, and negative 1, 0. All right, so by looking at the graph and thinking about it, I want to find the area here, which is going to be the integral between 0 and negative 1, and then double it to also get the area of that region. All right, so there's my plan. There's how I can use the graph and the rules that I know in order to calculate this without having to go and do any bashing my head against the wall. All right, let's head back over to the notebook and let's set up exactly that. We said that the area here is going to be 2 times the integral from negative 1 to 0 of x cubed minus x dx. We can perform that integration. It's a polynomial, so we'll just apply the power rule to each term individually. So we'll have 1/4 x to the 4th, and we'll have 1/2 x squared. We'll evaluate at negative 1, we'll evaluate at 0. All right, plugging in x equals 0 will give us, well, 0. Plugging in x equals negative 1. Negative 1 to the 4th power is 1. Negative 1 to the 2nd power is 1. 1/4 minus 1/2 is negative 1/2. 0 minus negative 1/2 is positive 1/2. and then 1/2 times 2 is 1. The total area of those two little slivers on the graph is 1. All right. Um, so again, nothing really new here. We've talked about area under a curve before. We've talked about positive and negative integrals before. We've talked about even and odd functions before, throwing it all together in one place. So that's really all I have to talk about. Let's wrap up with a problem like this for you to try. This one might be a little bit simpler than the one I just went through. I would like you to calculate the area bounded by the x-axis and the curve y equals 4 minus x squared. First, use Desmos or a tool like that to graph and figure out exactly what this region looks like, and then see what you can do. And you might want to go back and revisit the fact that we looked at this in an approximation case as one of our early examples talking about the Riemann sum. So here we can find the exact value. We have all the tools and find it a lot more readily than that definition we had before. All right, take a few minutes, see what you can do with this one, and I'll see you in the next video.